Good morning. My name's Nigel Turvey from Western Power Distribution. I'm the Network Strategy and Innovation Manager here. Welcome to our webinar to go through the strategic study work that we've done in South Wales. The full report is available from our website, but I will try and give some context to it with this presentation. So if I start off with just highlighting what the objectives of doing this study were. First off, we were trying to understand the potential growth in demand and generation over the next effectively about 15 years. And to do that, we've looked at 4 economic scenarios to try and give us an envelope of how demand and generation may grow. From that, the process was to assess the capabilities of the network to actually operate under those scenarios and to understand where we run into issues in terms of network capacity or voltage to allow that to continue to grow. From there, it was to assess where we have problems, to assess what reinforcement might be needed to accommodate that growth. And the purpose of that really is to provide feedback to stakeholders of likely constraints on the network, and also to look at whether there are particular aspects of development which are worth progressing because they are sort of low regret. One thing to just mention at this stage, there is a web chat option on the webinar. So therefore, if you have any questions, if you can put them in through that, when I get to the end, I will seek to try and answer as many of those as I can. To give some sort of context to the study, looking at the network in South Wales, it was obviously designed around demand. So it's designed for a one-way flow of electricity down to demand. And we have a current maximum demand of just over 2 gigawatts at winter peak, with a minimum demand, generally in the summer, just below a gigawatt. What we have seen in more recent times is a huge growth in distributed generation connected to the network, as shown in that table on the slide. So we have nearly 2 gigawatts of connected capacity of generation of different types, a significant amount of renewables. But we also have a lot of people that have accepted contracts for connection going forwards. And more recently, we've also begun to see the application of storage to connect to the network. And so, that's another technology coming in more recent times. What's actually happened is that the connection of that generation has used up the sort of inherent capacity to be able to connect to that network. And we've reached a point really where the cost and timescales to expand the network to allow more to connect leads generation to have some difficulties with continuing with that connection, and hence we have alternative connection arrangements in place which allow generation to connect provided they accept there are certain times when they can't export. But increasingly that has led people to either need to accept one of those sorts of offers or potentially to try and relocate their project to another part of Great Britain in terms of where there isn't the same sort of levels of constraint. And really continuing on from that, both those reinforcement requirements and issues which are also occurring on the transmission network, which are sort of exposed by a statement of works process where we make an application to National Grid, have caused uncertainty and difficulties for generation customers being able to commit to their projects and the investment in those projects. Now, whilst we are seeing volumes of applications for these large-scale connections have fallen in more recent times, mainly due to the change in subsidy and support arrangements from government, we are expecting that the cost of technology is falling, and hence we're expecting price parity probably within the next few years for some particularly like solar type technologies, and hence we could see a big uptake again of people seeking connection to the network. And that really reinforces the importance of doing this work of understanding the issues that may cause and being ready to know how to respond to that in terms of what might need to be done to the network. The other aspect, I think, which sort of backs up those comments is from Committee on Climate Change report last year, which is highlighting that whilst in the short term we're meeting the objectives on climate change, longer term there are still risks in terms of whether we're really achieving the reduction in carbon intensity of generation on the network, and they're looking for a better framework that these generators can come forward and seek contracts to actually export onto the network. And of course, if that framework comes in, that again reinforces the issue alongside falling cost in technology of potentially seeing a large growth in applications for further connections. In terms of the scenarios we've looked at, we have actually used the economic scenarios that were developed by National Grid as part of their future energy scenarios. So that's the economics, which really looks at this grid here of prosperity and green ambition, giving those sort of 4 scenarios of consumer power, gone green, no progression and slow progression. And what we've actually done then is looked at the South Wales situation in terms of what resources, etc., are there, to look at the growth that we might expect under those different scenarios of distributed generation, the use of electricity for heat, electric vehicle growth, and storage, as I say, a new technology that's been coming in more recently. In doing this, we've actually engaged Regen South West, who have done a lot of work with developers to understand the potential growth in these areas and how to fit those into these 4 scenarios. To give a little bit of background on the methodology that's been used to create those scenarios, for the different types of technology of distributed generation, for each one we've obviously done some work to make sure we do fully understand what's actually in the current baseline in terms of what's connected at the moment, by what technology, and where it's connected on the network, and also how that growth in that generation has happened over the last few years. We then looked at the short-term projection in terms of being able to look at things which are in progress. In other words, they either have planning consent or they've made an application to us, and we can actually start assessing under those different scenarios which ones are more likely to take place and actually go ahead, or which ones may not actually manage to get connected going forwards. Beyond that sort of near-term pipeline, we're then looking at the growth scenarios, which again takes into account the economic background of the scenarios, but also looks at the resource availability, planning consent processes in terms of what is the likely growth, what is the likely location of that growth as well across the network. To give an idea of the outputs which come from that, this first graph here shows the demand growth. As you can see, it's relatively flat for all the scenarios. The main reasons for that is, of course, we have a combination here going on of whilst there is a degree of generic growth in demand due to more houses being connected and just general development, but there's also an offsetting of energy efficiency going on, so the amount of energy used in those houses goes down as well. But the slight uptake that is shown in this demand graph is really driven from that electric vehicle and use of electricity for heat in terms of what's in there, and that's why the gone green really comes out as the higher demand growth, because there's an expectation of more take-up of electric vehicle type technologies. A fairly different picture on the growth of distributed generation, and again this is really driven very much by that economics and that green ambition in terms of how much uptake we might see. As you can see, we end up with a very significant envelope once we get out towards 2030 in terms of the possible range we might see looking at those economic scenarios. In order to take those scenarios forward and actually understand what impact that has on the network, we've taken the network we cover in South Wales and the area we cover is shown on that map and divided it into what we call electricity supply areas. And they're really shown by the black lines on that map in terms of the divisions between those different areas. They're really areas that we supply in terms of our supply points into those areas at 132 to 33 or 132 to 11 kV. And they really give us that sort of geographic area that we can look at to be able to do network studies. We focused the studies looking very much at the higher voltages on the network. So our interface with the national grid, the 132 kV network, and the 66 kV network, which are sort of the main sub-transmission voltages in South Wales. We've focused on those parts of the network because those elements have the longest time to do any work on in terms of reinforcement, and some of them where it needs new overhead lines or changes to overhead lines can involve quite protracted planning consent processes, and equally they're quite expensive. So therefore, we end up with quite long timescales on these. So that's why we focused on that in terms of what the impact was of those scenarios on the network. The other aspect that was slightly different in this study compared to what we've done in the past is, in the past we would generally study a single half-hour winter peak or summer minimum to understand what was going on. Because we're seeing changes in technology and changes in the mix of technology, the time at which we might see the peak demand or the minimum demand may change during the day. So therefore, we've actually looked at whole days, modelling each half hour. We've done that for 3 typical days in the years we studied, in terms of a summer day dominated by distributed generation, so you get quite a lot of export from the network. A winter day, which again is demand dominated, many renewables, for example PV, is exporting at quite low levels on winter days. And then typical sort of spring-autumn day, very much to look at the maintenance period when we're taking outages on the network to be able to do maintenance of it. The studies have looked at the network when it's intact, when it's got a single outage on it, but also when it's got overlapping outages, 2 outages on a piece of network at the same time, and busbar outages, so we can understand the full range of what might happen if things go wrong. The profiles we use for demand and generation, we've actually used a combination of looking at history, where we've got technology types out there that we can actually assess the profile we might see during the day of import and export. But equally, we then had to modify that for the technology additions we might see under each scenario. We've also had to model in here the amount of automation we have on the network. There are certain automatic actions that happen when faults happen. So if a fault happens on the network, there's a certain degree of automatic reconfiguration of the network. So therefore, in doing this work, we've had to look at those load management schemes and overload schemes and model those in there. We've done the analysis for, obviously, the baseline to make sure it lines up with the operation we actually see, and then for scenarios looking at 2020 and 2025 to give us that forward-looking view. To give a sort of very brief overview of the results here, the full details are actually in the report on our website, but I'll just run through some of the very high-level sort of bigger areas where there's issues which come out of the scenarios when we look forward. Starting over in the west, Pembroke. It's an area which is very reliant on interconnection between our 132 kV to 33 kV connection points on the network. The issues are driven by the growth in DG that we're seeing there, and the potential reinforcements that are needed to accommodate the growth under those scenarios include reprofiling overhead lines. What this actually is where we're trying to operate the overhead line at a higher temperature so that we can get more current through that line to get more capacity. But in doing that, the line will sag more. So therefore, we have to look at ground clearance and make sure the line will not infringe ground clearance and won't cause any issues. So therefore, we have a certain degree of reprofiling to do. Clearly, where there's cables involved, 132 kV cables, we have little choice once they reach capacity, but to enhance their rating by overlaying them, laying a new cable, usually on the similar route. And then there's also issues in the transformation between different voltage levels, being able to get that power back out of the network. And so therefore we end up with a certain amount of transformer replacement. And because of some of the interconnection issues that we have, and trying to make sure we can keep control of the network as we have these higher network flows, there is some reconfiguration of the 33 kV network needed. Looking at the biggest electricity supply area we have, Swansea North. It's an area sort of more in the middle of South Wales. It's again very reliant in our rural areas on interconnection at 33 kV. Again, this area is driven by the growth in DG. We have many of the similar issues that we saw in the Pembroke area, but in here we also have the additional potential need of installing a further interconnection to the transmission network, a new grid supply point in this area, to relieve the very large grid supply point we have at Swansea North. Moving across to the RASA network, more into the sort of east of our South Wales patch. We have 66 kV networks supplying a large area on the outskirts of Newport and goes up into rural mid Wales. We have issues both on demand and generation here. And here, because voltage starts to become an issue on this network, we are looking at technology along the lines of what's called a STATCOM. What this is, it's a power electronics driven piece of equipment, look at using capacitors and reactors in effect to actually change the reactive power flows on this network, which help change the voltage on that network. So therefore, these are a piece of technology which can help alleviate some of those problems without building more overhead lines. So that's an area of here where slightly different technology will be needed to actually deal with the issues. The sort of Margam Pyle areas, we have here an area of significant wind resource in the Liffey Valley, which has a 66 kV network. It is very much connections that are seeking connection in that area. We end up with offers which look at separate new lines to them, and we really do need to look a bit more about whether there is the ability to share some assets in that area and potentially put single 132 kV lines into this area to actually reduce the need for the number of overhead lines that might be needed to enhance it. There are issues in that in terms of there are slightly different planning consent processes, and the planning consent process for 132 kV lines can be a bit more protracted. So therefore, coordinating that with the developer's needs in terms of the timescales they need to be able to connect can be an issue in terms of going forwards. So again, understanding the issues here helps to lay out some of those timetables that might be needed. So if I sort of summarize the results that we've got that are detailed in the report, it's very heavily scenario dependent. I've highlighted the big areas, if you like, the ones where we saw major issues, but there are also other issues identified in many of the other grid supply point groups listed on that slide. Most of this is driven by that significant growth in generation that we saw under those scenarios in an earlier slide, but there are still some demand-driven requirements in terms of more localized issues that we see. In terms of allowing generation to connect, I mean, one of the options to try and avoid some of this reinforcement is the use of active network management. What this actually does is it monitors the network in real time, looks at constraint points, looks at the output from different generators, and then can send signals to certain generators and say, well, if you constrain back, the network will continue to operate properly. So therefore, the connection offer to a customer is one on the basis of you can connect quicker because there is less work to do on the network. You can connect without having to contribute to reinforcement of the network, so you get a lower cost connection, but the penalty is that you may be constrained at certain times. So in terms of using active network management, there is clearly a commercial limit on the amount of curtailment people can accept. So, when we make these offers, we make the best estimate we can of the potential curtailment people might see, but there is no guarantees on the upper limit on this. So therefore, the generator has to make an assessment as to whether that's an acceptable commercial term that they can use. But clearly, as that curtailment percentage expectation rises, it reaches a point where the generator can say it's really uneconomic for me to continue with this project. There are also some technical limits on how much we can connect under an active network management system. Clearly, the more complex the network gets, the more we end up with overlapping issues, which can end up causing high levels of constraint on generators, which again would make those connections uneconomic. So therefore, we need to be careful about how complex we make some of these schemes. We're also, by doing this, increasing the utilization of assets. So we're actually loading them up to higher levels for longer periods of time. And we do need to be careful about the ratings that we're actually using on that equipment. They're usually designed on the basis that they will have a cycle of loading, of high loading for short periods of time and then low loading. Now, clearly, the more we use things like active network management, the flatter the load curve becomes. So therefore, we have to be quite careful of understanding the ratings of the equipment under those conditions. We also have the issue of active network management is obviously sending signals to generation to constrain. Quite often, that's a constraint that will operate in minutes rather than seconds. And clearly, we do have system protection on the network, which will operate in seconds or sub-second timescales. So we have to make sure there is good coordination between these schemes to ensure that we don't have a system protection operation isolating parts of the network before the active network management scheme can actually operate. Where we do run into that sort of concern, we may have to do pre-curtailment of generation. In other words, we have to look forward and say, if this fault happened on the network, we would have to pre-curtail certain generation to make sure that wouldn't cause us an issue. I mentioned earlier that there are issues now on the transmission network in South Wales. We have this process called Statement of Works, which also includes a modification application process where we tell National Grid which generation is seeking to connect to the network and where. They do an assessment as to whether that will cause an issue on the transmission network. That has happened in South Wales, and a recent modification offers from Grid that we've received do highlight particular issues with connecting more thermal plants in South Wales. So this is generally plant powered by diesel or gas, and those further connections of those do actually cause National Grid some significant issues. The response to the modification application is to highlight some significant reinforcement works that would be required and quite long timescales to undertake that work. Now, as I say, that has been fairly recently received. We're reviewing that, and we're certainly communicating with the customers directly affected by that modification application in terms of their application to us. And so that's an ongoing process at the present time. Now, in addition to that, we are, and this is in the Southwest license area, working with National Grid to develop a regional development program. And in that, it's how we can coordinate the operation of the transmission and distribution network to minimize the issues as more generation connects and to release as much capacity as possible. So I say that's a process being developed at the moment in the Southwest license area, but the concept behind the program that we're doing with National Grid is to understand how we can do this to potentially roll that out into other areas of the network. In terms of the recommendations which have come out of the report, this is obviously looking out into the future in terms of if those growths happen in those scenarios, the type of activities that we would need to do in terms of reinforcement of those networks listed there. So if this growth that we see in these scenarios actually happens, there's a fair bit of work to do on the network, and that obviously feeds also into the recent call for evidence from BEIS and Ofgem, where they're looking for flexibility, so they're very much looking for further developments of active network management, but also in terms of whether there's more response available from the demand side to help avoid or delay some of these reinforcements on the network. Again, in terms of recommendations from the report, we obviously need to do that further assessment with National Grid in terms of whether those longer term scenarios cause further issues for National Grid beyond those that have been identified in the modification application. We're also looking at making sure we do fully understand the technical limits of some of the active network management and automation we're putting on the network to ensure we're releasing as much capacity as we can without causing a risk to the future operation of the network. And then finally, we're looking to repeat these studies every couple of years so that we keep up to date with actually how things are developing and actually what has been connected to the network. The other clearly key aspect to this is how it's paid for if reinforcement is needed. Well, as we speak today, we have a connection charging methodology which is approved by our regulator, which really says that when someone connects to the network and it triggers reinforcement, then a significant contribution is usually required from that connecting party towards the cost of that reinforcement. Now, obviously, that will continue, but just as a slight caveat to that, charging policy applies with what's called a voltage level rule. So in other words, if you connect a low voltage, more than one voltage level below where the issues occur on the network for reinforcement, you don't contribute towards the cost of that reinforcement. So therefore, what we are seeing is changes in that lower voltages where we're seeing small-scale generation connections and to some extent demand reduction due to ongoing energy efficiency and generation being connected behind the meter, reducing the demand we're seeing. So therefore, it's not always possible to actually identify exactly who has caused a reinforcement need. Clearly, when that happens, we'll still need to develop a network to make sure it can continue to operate effectively. And the costs of that will then end up being spread across all customers via tariffs. And we've certainly reached that point in certain parts of the network in the southwest, and there are some works going on which are funded in that way. And we're looking now at the South Wales results we've got out of this study in terms of where there might be reinforcements that we need to move forward on in South Wales. There are other issues which have sort of come out of doing the study work, just to that have sort of highlighted themselves in terms of how, as we've done things. First one, they are abnormal operating conditions. Whilst when people accept a connection to the network for generation, there is a right in there to constrain the generation when we have abnormal operating conditions. Now, clearly, we need to do more work on this to ensure that we minimize the amount of times this happened, and we can highlight to the generator the real risk that they're seeing. So they really want to know before they connect, what is the risk that I will be constrained for abnormal operating conditions? What sort of timescales might it be? How might it affect my long-term operation? And hence there are issues that we need to do there to help the generator better assess the risk it is taking in actually signing the connection offers. Part of that really is defining the commercial rights. And hence, is there a limit at which you should say, well, actually, this is beyond reasonable, and so therefore there should be some sort of compensation mechanism. And that's something that is being looked at nationally as well in terms of how we might frame the ongoing commercial rights associated with generators when they accept these connection terms. P2 is the demand security standard. That is currently under review to understand the amount of network capacity that is needed to ensure that demand is as secure as it possibly can be, and we end up with good performance in terms of small numbers of power cuts. That is currently under review. I have to say the results so far talk about there is no economic case for increasing the security of supply to generation connected to distribution networks. I mean, that's something we're looking at going forwards in terms of whether that changes as the balance of generation between transmission connected and distribution connected changes, as to whether that case will remain. Other issues which have come out of this are really about how we operate the network going forwards, and hence we're looking at producing a distribution system operability framework. This would sort of sit alongside a document that National Grid currently produce annually, the System Operability Framework. National Grid are already looking to try and incorporate some of the issues which come up from distribution in terms of including in that SOF. Just to sort of give a bit of background as to what we're looking to put in our distribution system operability framework, it's at the early stage of development, but to give a sort of framework as to how we're looking at it, we're looking at three main areas: the actual network, its performance, and then customer issues that we actually see on it. And what I show on this table on the slide is some of the issues that we're looking to include in that SOF. So things like how we model the network. We've had to do quite different things in terms of doing these strategic studies to understand what the issues are going out long term than we have done more traditionally. And it's really looking at what further capability might we need in that network modeling. And then across, perhaps on the customer side, dispatch coordination. In other words, how do we actually understand the curtailment that we might need going forwards to deal with maintenance outages and fault outages, and how do we ensure customers understand the risks they have in terms of the length of time or locations they might see those. So to summarize what we've done in this report is it's really the first time we've undertaken quite such a long-term comprehensive analysis of the network in South Wales. We've looked at quite a significant envelope of potential change in both generation and demand to try and understand the issues that will arise, but then also to give a very high-level view of the potential solutions that there might be to actually deal with those. We're also looking to do further work with the National Grid to make sure that we incorporate the transmission issues that might occur as well. The work has highlighted some of the operability issues that we will see going forwards, and we're looking at developing this distribution system operability framework to actually deal with those and what timescale they need to be dealt with and what potentially some of the solutions might be to those. We're continuing with the strategic study work. We're now moving on to our East Midlands network, which obviously we will incorporate things that we've learned as we've gone through doing the studies in both South West and South Wales, and hence this is part of a long-term cycle of assessment. So we're looking at assessing each of our licence areas on a sort of 2-year rolling basis so that we get the lessons learned as we do things, but also we understand how things are beginning to develop as we go forwards. And in those we can incorporate changing policy that we have that may come out of the Bayes Ofgem call for evidence on flexibility, but also as new technology comes out, we can learn how to incorporate those sorts of things. So operating modes we might see on storage and how that affects the network and its operation. So, I mean, that's all I've got to say on the presentation. So thank you for listening to that. I will now move on to look at some of the questions that have been raised and see if I can actually answer any of the issues. So, if I start with potential marine generation, question that's come in. The issue really on marine generation is that as far as whilst there are some smaller demonstration projects going in terms of large-scale marine projects, The only one we're really aware of is the tidal barrage type issues in South Wales. And certainly the one that's being looked at developing the Swansea area is looking to connect directly to the transmission network, so therefore isn't really an issue for us. But clearly, given the tidal range of the River Severn, there are significant opportunities, and some of the tidal flow off the west coast of Wales present opportunities as well for tidal flow type schemes. We have had developers approach us looking at those, and we have made connection offers. However, we think the technology still has a little way to go yet in terms of some of the tidal flow ones. Clearly, the barrage is really more of an economic cost issue. I think the technology is well developed, and it's purely an economic one. So we may well see some of those come forwards. In terms of, all right, let me look at what else we've got. Principles for undergrounding land connection points for any marine generation. Well, again, we're just subject to normal land right issues in terms of generally we will have to seek consent from the affected landowners, and including Crown Estate as you get to the coastline. And hence it's really a consent process, permission process in terms of dealing with that. There's one here on looking at what body or organisation is looking at the commercial rights for generators. What we have got under our trade association, the Electricity Networks Association, we've just started a fairly major project looking at a number of things, but one of them is the interface between transmission and distribution networks. The second part of it is the transition from DNO to distribution system operator, and then also looking at sort of the customer experience in terms of how they actually interface with the industry, and then finally also on charging. And hence it is under that group that we're looking at picking up properly understanding the commercial rights. And it is actually things like what do we mean when you get connection offers which give you a constrained or unconstrained or an alternative connection offer or a firm, non-firm. What do we actually mean by those? What rights do people actually signing up to when they actually get those sorts of offers? And trying to make sure that there is a more common understanding in terms of how that works. So that will be working under that group. We are looking to try and disseminate information from that group via various means in terms of workshops, in terms of additions to our Trade Association website, and newsletters and those sorts of media of actually distributing information. We're also looking to have an advisory group sitting alongside what we're doing on that work to involve stakeholders from as many different types of stakeholders, customers as we can, so that we can feedback what we're doing on that project, and they can feedback to us where they think we're missing things or where we're perhaps going down wrong tracks. Another question was, if we make anticipatory reinforcement, would a new connection that was enabled by the reinforcement be subject to some form of second comer charge? It really depends on the way in which the anticipatory reinforcement is actually done. If it was just done on the basis of we had no connections accepting an offer, then the rules do not allow us to charge that on to a second comer. In other words, if we actually do it purely as it is our view this reinforcement is needed, then that cost is spread across the entire customer base via system tariffs. However, under the quicker, more efficient connections process that Ofgem have been running, what we have saw recently in WPD is a derogation to the charging methodology, whereby we can end up in situations where we're pretty sure that a large-scale reinforcement is needed in an area. Someone applies for connection in that area, and rather than applying the whole cost of that reinforcement to that connection, this derogation would allow us to charge a proportion of it, in other words, proportion down to the amount of capacity they're asking for. In those circumstances, clearly, if you then get other connections, we can charge as sort of a second comer rule. In other words, we can recover other parts of that reinforcement from subsequent connectees over a timescale which is currently 5 years. In other words, people connect within 5 years of that happening. But there is proposals for legislation going through which will extend that out to 10 years. Next one was, could you please elaborate on the A&M aspects considered? Has batteries, demand response, StatCom considered? So I think in this area, it's what does active network management apply to? At the moment, it's very much being focused on connecting distributed generation. The way it's being designed, though, doesn't actually restrict it to distributed generation. We can expand that to incorporate storage. We can expand that to incorporate demand if necessary. So therefore, the technology that's been put in allows any of those things to happen. So therefore, we would actually use that wherever we can. The next one is, has the cost of establishing active network management against reinforcement costs been weighted, and if so, how? In other words, how have we decided this is an economic response to the issues? I think that's to some extent work in progress. The reason we have gone down the road of producing active network management was that customers needed to be able to connect quickly. A lot of that was driven by their project timescales and by subsidy arrangements and concerns that subsidies were going to be reduced or removed. So therefore, people needed to be able to connect quickly. And the active network management technology allowed those connections to happen quickly. Now, clearly, as I think is behind the question, there is the, if you like, economics for Great Britain in terms of is the curtailment of that generation and the lost output actually worth more than it would have cost to do the reinforcement? That is actually an aspect that is we're looking at under our regional development plan that we're doing in the Southwest. We're trying to look at more the whole system cost in terms of what is the balance in terms of when you look at curtailment of generation as opposed to reinforcement of the network. This is also being looked at in the project under our trade association, the one I was describing earlier, in terms of investment planning and how you look across the boundary between transmission distribution and decide where investment is made or if it needs to be made or whether there's an operational solution or potentially curtailment of generation which is better. Now, at the present time, there are different rules between transmission and distribution on how compensation is undertaken. Certainly the distribution level, we don't pay compensation for curtailment of generation. It is seen that the benefit was in being able to obtain a connection either quicker or at lower cost by not having to contribute to reinforcement. Whereas at transmission, there is a constraint payment process. So therefore, there are differences between these, and we need to build that into how the investment appraisal works to understand whether it's appropriate to continue with more active network management and higher levels of constraint, or whether you've reached the point where you actually need to build more network to avoid that. Next one. How did you overlay non-intact network conditions versus each of the day's 48 half-hour modeled intervals? I'm just going to hand over to a colleague who's going to have a go at answering that one.
Hello, Steve Quinn from Western Power here. So looking at this question and the follow-up, did you choose specific moments of stress and how were these justified? We actually took quite a broad approach to this. where we tried every n-1 or first circuit outage condition against every half hour of every representative day. And then we also tried every busbar outage against every half hour of every representative day and every second circuit outage, so combination of 2 first circuit outages against every half hour of every representative day, and looked for where the worst results came in. Now, traditionally, planners would do this by spotting what they think would be the worst cases, and mostly we came out with the same answers, but interestingly, occasionally we found issues, particularly around reactive power flows, where things were turning up at unexpected times of day. So I think taking that broad approach, which did take a while to compute, was quite justified by that.
Okay, thank you, Steve. So the next one is about quantification of modelled constraints. Now, I think here, because we've done 3 representative days, this is quite difficult. I mean, obviously, we can understand the quantity of constraint on a particular day. I mean, I think what this particular question is driving at is the issue of how much energy actually needs to be displaced to deal with some of these constraint issues. So this is particularly looking at the storage market and the potential for storage to help solve some of these network solutions, some of these network issues that we're seeing. What I want to do is to start looking further at these studies as to how we do model the amount of energy that would need to be shifted to deal with some of these issues. Now, clearly, the studies we've done to date aren't really adequate to do that because they're just looking at 3 representative days. We would need to expand that to cover more of the year to actually try and start understanding the amount of energy that would need to be displaced to deal with some of these issues and whether storage could be a potential solution. But equally, the amount of demand-side response that might be needed to deal with some of these solutions. So again, whether the customer is in a position to be able to give the demand response for the length of time that we would actually need to deal with those issues. So I think that is a follow-on piece of work that we need to do in terms of looking at this. Is probably our second cycle of doing this work. It is an area I'm quite conscious of. As we do this, we're finding more and more aspects where we need to expand how we look at this work. All right. The next one was, can or will Western Power utilize smart inverters to provide voltage support to the network? And then there's another one which is very similar, which is on STATCOM solutions. Instead of could we procure reactive power from generators or storage, and could that be more economic than building more network? Now, I think the answer to both those questions is a definite yes, in terms it has the potential. Certainly, our understanding of the inverter technology is that if it's not highly loaded, which clearly at many times of the day it isn't highly loaded, it has the potential to operate at quite a wide range of power factors and hence supply reactive power or absorb reactive power from the network. And to that extent, we are trying to get a project off the ground at the moment to start developing reactive power services in terms of looking at the response we can actually get, how useful that is to the network. So it is definitely an area that we need to develop, and I'm sure that the marginal cost of operating inverters in this way will be relatively low, and certainly lower than many of the network solutions that we might end up with in terms of doing that. Now, clearly in doing that, we still need to make sure that that reactive power service is available when we need it. So it may be that there's a degree of combination of you need a certain degree of assets on the network, as in a STATCOM, but supplemented with commercial services from generators or storage operators who are able to provide those services. Next one is how can the uncertainty of industrial customers, for example, steelworks, going green be accommodated and taken into consideration? So I assume that behind this is more the uncertainty of the amount of demand that we will actually see on the network, and clearly customers like steelworks are very significant demands on the network, so therefore we can end up with quite sudden changes. This is a significant risk that we face. I mean, particularly as we've been adding generation to the network, we've been making assumptions about the amount of demand there is to absorb a certain amount of that generation locally. So therefore, developing flexible services becomes very important to us in terms of being able to react to that. We do try and look at networks where we have, very significant customers, slightly differently to the generality of networks, in terms of we do try and look at that consideration of sudden loss of single customers. But yes, it is a risk going forwards. We can only try and model it and understand it. And as I say, development of flexible services and generation constraint processes are clearly going to be an important part of being able to accommodate potentially quite sudden changes in the way demand operates. Next one is in terms of the recommendations we have we actually mapped things out schematically so that people can see it on a geographic basis? We haven't at present. I mean, it is something we did think about ourselves in terms of, well, perhaps that is a good idea that we actually need to look at in terms of giving a representation of the areas of concern, and giving some sort of geographic representation of where we might see solutions going forwards. In terms of the next question, what are the specific issues that grid have with connecting new thermal plant in the region? What is the solution? Again, as I said, we're still fully analysing the modification application response we've had from National Grid, but it is certainly being able to export at winter peak from the South Wales network. Certainly the solutions in the modification offer we've received from National Grid are significant asset works on the National Grid system, which are going to be both quite expensive but also going to take quite a long time to implement. So as I said earlier, we're responding and communicating with the customers immediately affected because they have a connection offer which is affected by this modification application at the present time, and we'll communicate more information as soon as we've got the full analysis in and are able to do so. Next question is looking at whether there's an alternative to network reinforcement of effectively private wire connections between industrial customers and local distributed generations being used to offset the load on the network. Well, in many ways, we're already seeing this. We're already seeing quite a lot of generation being connected behind the meter, and that's particularly a response to the change in subsidy and support arrangements. Clearly, if you are offsetting the energy usage in a customer's premise before it reaches, it actually has to import stuff via the meter, then clearly it's of more value than the price you would get by just selling it into the wholesale market if you were connected to the distribution network. And so therefore there is already a strong incentive for people to do this, and we are seeing this happen. And that is one of the reasons we are seeing a certain degree of demand reduction as we go forwards. Now clearly, if the generation has a sort of output which matches the demand, then clearly that can be quite beneficial to the network. Quite often that isn't the case, and hence we're still going to see similar loads on the network at certain times. It will just perhaps be of a lower utilization. So therefore, we have to be quite careful in terms of understanding that. And that's why we're very keen to understand what has been connected where, what capacity, its type of technology, so that we can start understanding the potential behavior we might see on the network to be able to forecast what we need to do to the network. There are issues clearly for policy in terms of a government level in terms of this, because clearly if you get lots of private networks which extend potentially beyond the premise boundaries, then clearly there is a, if you like, a public policy issue of, do we want unlicensed networks going across public ground or in highways or anything else in the longer term or not? So therefore, that's an issue that I suspect government policy will look at some point in terms of the degree to which this is the direction they want to go in. And then finally on here at the moment, I've got, having undertaken this exercise, is there now a top priority list of low, no regret reinforcement? Can WP proceed with these straight away, or is legislation change required? We are, well, if I put this in context, if I look at the Southwest, we finished that study 6 months ago, and I mean, out of that, there has already been some work that has been initiated. Some of that was sort of prior to that strategic study being done, like work on the F route, which was a 132 kV line interconnection into the Southwest. But we are also looking now at upgrading a 132 kV route down the west coast of the Southwest, a line called the K route. And in that, we're actually overlaying a cable under the River Torridge and looking at reprofiling the 132 kV line to get more capacity out of it. We are doing works down at a major substation in Cornwall, a place called Fradden, of putting more transformer capacity in. Those are all strategic reinforcements which to some extent have come out partly of that strategic study, but some of them were pre-existing and had been started before that. We're looking through the South Wales report at the moment just to understand which ones we will take forward. The intent is that there are some in there that we believe do need to go forwards, and we don't believe we need any legislation change to do that. We can actually get on with it and undertake some of that works. Now, clearly that won't release significant capacity because we are looking at networks where we are already suffering significant issues or constraints that we would actually be looking to do something on. But we will clearly let people know as soon as we're able to on what those are. But I say we only finished this report fairly recently, and we're still assessing internally which ones to take forward, as we believe they are very low risk in terms of ending up as being stranded assets which are underutilized. Right, I think I've been through all of the questions that have come through. In terms of the presentation, I've just put up a slide which gives the location of the actual investment study and also gives an email address for any further questions that you think of or come across afterwards, or once you start reading the report that you want answered. So if you send them into that email address, we'll get back to you as soon as we can with the best answer we can at the time. I'll just pause a second just to make sure there's nothing else, but it doesn't look like there is. In which case, I just want to thank you for joining our webinar, listening to me and posing your questions. Hopefully I've managed to answer them reasonably comprehensively. So thank you all very much. As I said, we're continuing this study work with the other license areas we have, and there will be a refresh of these. So thank you very much.